Hi guys, so today we are going to talk about endogeneity. Endogeneity is the hidden threat in your regression results. To start with, the reason I started this YouTube channel because at the point I wasn't really understanding what most of my professors were saying, and they use these big words and that I don't even understand what they mean. I don't know how you can come to class and you use a word like endogeneity freely, expecting me to know what endogeneity is, and without defining and clarifying their meaning, so I can actually follow through the class. So I decided to just do my own readings and dig deep, and also help people through my videos. And because endogeneity is such an advanced topic, I will be using other words to explain it. But I'll try my best to, whenever I use any ambiguous word, maybe do a video to explain what it means. So because I don't want this video to get too long. So like I said, um, today we're going to be talking about one of the most important concepts in econometrics, which is endogeneity. So if you're studying information systems, business analytics, or any field that uses regression analysis, understanding endogeneity is absolutely critical. And this is the hidden threat that can completely ruin your regression results without you even knowing. So by the end of this video, you know how to spot it, diagnose it, and fix it. So I said a lot of things. I said regression. If you don't understand what a regression is, I'll do a video and add to this video so you can understand. And that's it. So, so what is? Let me keep my face here so you can see me. So, what exactly is endogeneity? Here's a simple example. Endogeneity occurs when your predictor variable. So, in research we have independent and dependent, and X is independent and Y is dependent. So, X causes Y. So, it's all about measuring causality. If you don't understand this, I have a video for it, which I will link here. So, like I said, endogeneity occurs when your predictor variable, independent variable, that is your x, is correlated with an error term in your regression. Now, what does this mean in plain English? Think of this, think of this, think of it in this way. You're trying to measure how x affects y, but x itself is being influenced by some hidden factors that you haven't accounted for. We saw X affects Y, but X is influenced by some hidden factors. So this creates a tangled up mess where you can't tell the true relationship is. And here's why this matter. Look at the consequences on the here on your right side. Now, the consequences are that you get a very biased coefficient. If you don't know what a coefficient is, I'll do a video and let me write it down. So I said things, independent variable, I said coefficient, I said regression. So now your coefficient will be very biased and your estimates will be systematically wrong. And you will be measuring the wrong relationships. So here's a big picture. I like to think of endogeneity using a medical analogy because it really helps clarify what is going on. So endogeneity itself, let's say endogeneity is fever. And if the symptoms you observe, and if the symptoms you observe, specifically you observe that the X is correlated with an error term, this this gives you a biased result, right? But just like fever can have different causes, you know, let's say endogeneity is the fever. Fever can have different causes. Endogeneity has three main causes. So endogeneity is a disease. Let's say it's fever. It can be diabetes. It can be anything. So what are the causes of diabetes? You know, what are the causes of fever? So what are the causes of endogeneity? So the first cause of endogeneity is reverse causality. Number two is omitted variable bias. And number three is measurement error. So reverse causality is basically originally we expect X to cause Y, the independent variable to cause the dependent variable. But what if the dependent variable is not causing the independent variable? Why? What if Y causes X instead? The other way around. That's reverse causality. The second is omitted variable bias. This is when you forget to include an important variable Z in your model. You forget to include an important variable which is Z in your model, right? So here is how you have omitted variable bias. And number three is the measurement error. This is when your X variable is measured incorrectly. So just like a doctor needs to identify whether your fever is caused by flu, an infection, or something else, you need to diagnose which type of endogeneity you have before you can treat it properly. Let's go to the next slide. Now, let's talk about the reverse causality. Now, I have a very beautiful diagram here. So let's look at reverse causality. Look at this diagram. Originally, oh, oh my, I'm trying to say. Originally, you see, let's look at this diagram. You want X to cause Y, X to cause Y, right? This is a clean relationship, more like IT training leads to productivity, right? But this is one directional, right? But what if instead of X causing Y, you're getting a two-dimensional arrow where Y might be causing X? This is where you get a reverse causality. The relationship runs in both direction or even backwards from what you think. So this is the problem of reverse. So let me give you a few examples using information systems because my PhD is information systems. So this example will help make it crystal clear. Now, you might think you might think that hiring more IT staffs causes more systems problem. But the reality is the opposite. System problem causes you to hire more IT staff. You see the causation runs backwards because you think that hiring more IT staff causes more systems problem, whereas that the system problem, which is the dependent variable, is the reason why you're hiring more staffs. So you see, there's a causal problem because it is reversed. Number two, you might think that security software causes more security incidents to be detected, but actually it is the other way around. Experiencing security incidents causes companies to install security software in the first place. Again, the dependent variable is causing the independent variable. Number three, you might think that CRM feature improves customer retention, but in reality, companies give higher value customer, the ones who are extremely loyal, access to better CRM features. So you can see it's reverse. So you see the pattern. So in each case, Y is actually causing X, right? I need to get this out. In this case, you can see that Y is actually causing X. You think that the CRM feature leads to customer retention, while high value customers get CRM feature. This causing this. Security software leads to more incident, whereas more incidents leads to security software. More IT staff leads to system problems, whereas system problems leads to IT staff. So you see that now instead of X to cause Y, Y is causing X, which causes reverse causality. Number two is the omitted variable bias. Now, here is a very interesting part. Looking at this, and this is like actually the one of the most common types of endogeneity. And look at this diagram. You're measuring the relationship between X and Y, right? And the problem here is now the relationship is here is at the bottom, X and Y, but you're missing the hidden variable Z on the red box at the top. How do I mean? Now, Z might affect both X and Y through these hidden arrows. So, through these dash arrows. So, you haven't included this in your model, which means there's a causality problem. So, here's the classic information systems example: IT training and employee productivity. Let's say we say IT training is X and employee productivity, the dependent variable, is Y, right? You run a regression and you find that IT training increases productivity. Your coefficient might be 30, it might be so big, and you're like, wow, IT training increases productivity by 30. And you say, great news, you know? But, and in your mind, you're like, training really works. But you're omitting something. But wait, what are you missing? Employees' ability. The problem is employees' ability, Z. How is it a problem? Because as a company, you will likely send the most capable or the most brilliant employees to training, right? Because smart, capable employees are more likely to be selected for training in the first place. And you're also, and those people is not just that they are also that they are likely selected for training, which already affects the Z, the X, right? Which is IT training. They are also productive, which also affects the Y, the productivity. So you see that Z here, the red, is affecting this and this. So IT training here leads to more productivity. But you're forgetting that smart, productive employees are the ones that are sent to training. And it affects X and Y. And you do this regression and you say, yes, there's a relationship. But you're missing the hidden variable here. So your coefficients, which I'll explain, get so high and you're happy. but you're not getting the true impact of IT training, because smart people are productive and smart people get to be involved in training. These are the things that we don't check. So this is what is called omitted variable bias. So you are massively overestimating how training actually helps. So this is why omitted variable bias is a very dangerous thing. Your result looks convincing. They are telling the whole story, but whereas they are not. Now, measurement error. Now, I want you to take a look at this. This happens when the x variable is measured with error or inaccuracy, which is your independent variable. When it's measured with error, look at the examples on the screen. Now, the true training hours might be 40. Might be 40. But if you're using a self-reported data, people might say 50. There's already a measurement error. They are misremembering, exaggerating, or genuinely confused about what counts as training. So, what this do to your coefficients is it creates what we call atten called attenuation bias. The measurement error pulls the coefficients towards 0. So if the true effect is 20, your estimate might only be 12. You are misunderstanding the real relationship. This is super common. This is super common in information system research. Now, look at this example. Let's say users you create a user satisfaction survey. You have to understand that when it comes to user satisfaction, people lie or misunderstand questions. Self-reported app usage, people might have terrible memory about how much they actually use the app. About security incident, maybe some security incidents go unreported. About system downtime, it depends on how you define downtime. So anytime you rely on a survey, on a Likert scale, self-reporting, or imperfect tracking, you need to worry about measurement error causing endogeneity. Now, let's talk about how to diagnose endogeneity. Okay, so now you know the three types of endogeneity, but how do you actually diagnose it? You need to ask yourself three critical questions before running your regression. Let me walk you each one of it. Question 1. Could causation run backwards? This is your reverse causality. Ask yourself, do X cause Y? Ask yourself, does Y cause X instead of X causing Y? Are they simultaneously determined? For example, do system problem cause IT hiring, or does IT hiring cause system problem? Number 2, you have to ask yourself, what am I not measuring? This is the omitted variable check. Think hard, think hard. Is here an important factor Z that affects X and Y? Is it correlated with X? Or even is it correlated with Y? For instance, am I missing user ability, product quality, or market condition? Or like in our former example, employees productivity or employees smartness. Question 3, how accurate is my data? Is your measurement error, this is your measurement error check. Is your X variable measured correctly? Could there be a reporting error? Are your survey response accurate? Is your data usage complete? You have to be honest with yourself when answering this question. The integrity of your entire estimate depends on it. The treatment strategy. Now, once you have diagnosed what type of endogeneity you have, it's time to treat them. There, here are the key insights. You only treat the specific type you actually identify. Don't try to fix everything. Just fix what is broken, please. Look at the decision tree. After you run your diagnosis, you ask three questions. Do I have reverse causality? If yes, fix it. If no, skip it and move on. Do I have omitted variable bias? If yes, fix it. If no, skip it and move on. Do I have measurement error? If yes, fix it. If no, skip it and move on. You might just have you might just have one type of endogeneity. You might have to. You might really have all three. You might have none at all. In which case, congratulations, you are good to go. The bottom line here is this. Think of endogeneity like diagnosing a car problem. Your car won't start. That's a symptom you have. But you don't replace the battery, add gas, and fix the starter. You diagnose which one is the problem and fix that specific issue. Now, the same principle applies to endogeneity. You diagnose first, then treat what is actually wrong. So, what are the actual solutions? How do you fix each type of endogeneity? Let me walk you through the main approach. Now, I'm not going to go in detail in this approach because this approach also needs their own separate videos, which I will endeavor to do. Use instrumental variable. So, instrumental variable is finding a variable that affects x but not y directly. This is a topic for a new video. You can run randomized experiment, A/B test, where you randomly assign treatment. You can use a lagged variable using past values of x to predict y, or you can look at natural experiments. For omitted variable bias, the solution are simply adding the missing variable to your model. If you can measure it, use fixed effect with panel data to control for unchanging characteristics. Include control variable that proxy for the missing factor. Use matching techniques like propensity score matching. For measurement error, the best solution is to get data more accurate data. You can also use instrumental variable or use multiple measurement and avoid them to reduce noise, or use validated scales and instrument that has been tested for accuracy. Again, different solution call for different situation call for different solution. The key is matching the right solution to the specific endogeneity you diagnose. Then well, let's use this real case study. And let me show you a real example of what happened when you ignore endogeneity versus when you properly account for it. Let's say we have a research question: does IT training increase employee productivity? And this is a simple regression technique. You have typical one independent variable and one dependent variable, and the independent variable IT training and employee productivity, the dependent variable. Now look at the naive approach here. The naive approach. Sorry, the tech is modded up. That's the wrong approach. You run a simple regression equation. This here is a simple regression equation. Sorry. This is a simple regression equation where you have y. Y is the productivity equals to the intercept is a and the coefficient is 30 and the dependent variable is training. This is a simple regression equation. If you don't understand this, the equation goes y being the independent variable equals to the intercept plus coefficient then dependent variable x. So on our video on regression, which I intend to do after this, I have all those there. So you can see now you are using training, IT training, to check for productivity, but we have a reverse causality here because productive employee get training, which means that here x might be causing, which means that um, this y dependent variable which means that y the dependent variable might be causing the training because productive employee gets training, not training, which is the independent variable causing this. So we have a reverse causality case here. So we also have an issue of omitted variable, which because employee ability can lead to training, and employee ability also um, employees which are smart and have the ability are productive, and employees who have the ability get to training. So you see that employee ability can cause both. So we are missing that is a z omitted variable. So the correct approach here is so if you look at it, you're seeing high coefficient 30, which is so much, and in your mind, wow, training leads to productivity, but it can be deceiving. The coefficient is biased, hugely biased. But here you can see the coefficient reduced to 10 when you actually check for endogeneity. And how you check for endogeneity, fixing the reverse causality, you can do a random assignment to training. So basically now uh, you randomly assign people to training to fix the reverse causality. So now you are very very careful to make sure that you don't assign productive employees to training. So you control for pre-training productivity score to account for this ability. So you see here the coefficient is now 10 as opposed to 30. Although there's a positive result, but we can say that IT training leads to productivity, but not that much, just as this one we did here. So ignoring endogeneity leads to overstating training impact by 200%. This could lead to massive budget misallocation. So here endogeneity. Before we wrap up, I also want to introduce you to other things briefly. Endogeneity, the problem is that x is correlated with an error term. The effect is that your coefficient is biased. They are systematically wrong. The main fix is using instrumental variables or experiments. Multicollinearity, which we'll talk about on the video, the problem is that your x variable are correlated with each other. Two x variable being correlated is multicollinearity. The effect is that your coefficients are imprecise, they are uncertain with large standard errors. To fix this, you remove or combine your x variables. Heteroscedasticity. Skedasticity. The problem is that your error variance change across different value. The effect is that your standard error are wrong, not your coefficient. To fix this, use robust standard error, which we're going to cover in subsequent class. Autocorrection. The problem is that your error are correlated over time. Again, it affects your standard error, not your coefficient. To fix this, you use time series model. Here's a critical distinction you need to remember. Endogeneity means estimates are wrong, they are biased. Multicollinearity means your estimates are uncertain. They might be right, but you can't tell. Heteroscedasticity and autocorrection means your confidence interval and p-values are wrong, but your coefficient might still be okay. So, alright, let's give you a practical checklist. You can use this before running any regression. Print this out. So put it on your wall, you know, check one. You could causation wrong backwards. Could x cause y instead of y causing x? If yes, you need to consider instrumental variables, experiment, or lagged variables. Check two. Am I missing any important variable that affects x and y? If yes, you need to add control variables or use fixed effects. Check 3. Is your variable measured accurately? If no, you need to get better data or use instrumental variable. And check 4. If I run a random experiment, would my result be different? Is there a great gut check? If you think randomize will give you different answers, you probably have endogeneity. Check 5. Do coefficients make theoretical sense? If your results are surprising or don't match what you what you expect based on theory, check all types of endogeneity. Run this check every single time. It takes 2 minutes and could save you from pushing completely wrong results. Key takeaways. Key takeaways. Number one, endogeneity means x is corrected with an error term, which leads to bias coefficients. There are three causes: reverse causality, omitted variable, and measurement error. Always diagnose before running your regression. Don't skip the step. It's like pilot doing a pre-flight check is optional. Only treat the specific type or types you identify. Don't apply solution randomly. Be methodological. Ignoring endogeneity can lead to completely wrong conclusion. This isn't a minor issue. It can invalidate your study. When in doubt, use instrumental variable or run an experiment. These are great and more powerful tools for dealing with endogeneity. If you remember nothing else from this video, remember good econometrics is about thinking critically before you run regression. It's about asking what could go wrong. And finally, remember. I want to leave you with one thought. Good regression analysis isn't just about running the model. It's about knowing which button to click in. It's not about knowing which button to click on STATA X on Excel. Good regression is about thinking critically about what might bias your result. It's about being intellectually honest with yourself about limitations of your data and your model. Master endogeneity and you avoid all most common errors and most serious mistakes in econometrics. You produce research that are reliable, you make business decisions based on accurate information, and you stand out from everyone else who is just running regression without thinking about whether their results are actually valid. Thank you for watching. if this helped you understand endogeneity, please like and subscribe. Leave a comment if you have a question. I read through every single one and I will help you walk through any confusion. And remember, always diagnose before you analyze. Good luck with your studies. Thank you.